every other distribution in statistics. And that's why I wanted to pay attention. Uh, I want to introduce you to normal distributions. And of course, what I'm going to do, okay, I'm going to walk you through. I'm going to start my explanation of normal distribution from, going historical. I want to go historical, okay? I'm going to start, all the way from, from up north, when you talk about divine providence, I'm going to go all the way to Galileo Galilei, going all the way to De Moivre's, Laplace, and Gauss, about because now this is the situation. Let me first introduce you to normal distribution. Okay, normal distribution is actually uh, one of the continuous probability distributions that we have. And of course, like I said, it's actually, it's often used or widely used in the field of science because of its simplicity. Okay, now take a look at this. Just like every other probability distribution, the normal distribution has a probability density function. Take a look at that. That's a probability density function. Okay, the normal distribution actually depends on two parameters. The two parameters, mu and sigma. Mu is the mean, which we also call Serra. Okay, and sigma is the standard deviation. Okay, and of course, the state space of a normal distribution is between a negative infinity and a positive infinity. Okay, and I'm also going to show you the shape of a normal distribution. Take a look at what you can see right now. Okay, we got two different probability curve here. You can see here. Okay, if you take a look at this guy actually have a low degree of disparity. It's shrinking. But if you take a look at this guy, that guy is spread out. Okay, even though the two curves are normal distribution curve, in one the standard deviation is actually high, and in the other is very very small. But let me first start with this, and I need you to pay attention. You know, I first want to start with the history. Okay, something we don't just do what we do. There's a reason why we do what we do. Okay, and I need you to pay attention right now. Okay, I'm actually want to start. I want to start with the history of normal distribution. When you talk about development of normal distribution, okay, it can actually be traced, to the to three completely different directions. But let me do this. Okay, please pay attention. I want to talk about history, okay, of normal, okay, distribution, okay, and that can be traced to the work of De Moivre, okay, De Moivre in 1733, and Laplace, okay, Laplace in 1783, and Gauss in 1809. Okay, I'm actually going to explain this one after the other. Okay, now, but something happened prior to 1733. Okay, there was a philosopher that we actually call Hopnot. Okay, Hopnot actually have divine arguments about this guy had a divine argument about the numbers of births. He compare male bat we compare male bat. He believed that male and female female bats, okay, male and female bats are near the same, okay, near the same rates, okay. According to Hobnot, he argue, he's actually taking his observation, observing constant in the regularity, okay, of male and female bats, and he actually conducted a study. He observed the numbers of male bats and female bats. I think between 1629 and 1702, okay, which is 82 years, and this guy believed that the probability that we're going to have more males than females is this. Okay, male and female, of course, the natural probability occur 1/2, right? Okay, and 1/2 raised to power 82, because he look at it for 82 years. Okay, we talk about constant. You remember what we did under binomial distribution. This is a binomial process because it could be, because we have two possible outcomes. He said that male or female, and since we talk about constant from year to year, because we believe that the male bat, the female, the ratio is actually going to be constant from year to, for 82 years. It's going to be this. When you look at this 1/2 raised to power 82, that would be nearly zero, right? That would be 0.00. So which means is this guy give the probability that male will be more than female is going to be this. So if the probability that male bar will be more than female is going to be this, then he's trying to say it's not likely that the number of male bar will be more. And this guy was actually argued that the nature is designed for monogamous pairing. Okay, monogamous. Okay, monogamous pairing. Okay, compared to polygamy, because he actually believed that with this, polygamy is contrary to the law of nature, according to this guy. Okay, but that doesn't mean this doesn't mean that polygamy is not natural. That doesn't prove that polygamy is not natural. But we're just trying to say looking at things, maybe the world is designed for monogamous pairing. But you know what? This guy does not really understand how to use binomial distribution. Okay, but you know what? Somebody that actually have a lot of patience among them, we call Grace Sandy. Okay, Grace Sandy now want to observe and really want to see whether he should go by this, and because Grace Sandy has some knowledge of binomial, okay, he's actually seeing the whole thing as a binomial process. And do you know, for 82 years, this guy, okay, studied the numbers of bats between male and female for 82 years, and in each year he collected a sample size of 11,492. Okay, 11,492 or 429. Sorry, 429. Okay, 429. Of course, P. What is P? P remains 0.5, right? And this guy noticed in the lowest ratio occur in 1703. In 1703, he has a lowest ratio, and that lowest ratio was 0.5029, and that is 0.5029. X, X represent the numbers of male bat. I think the numbers of male bat at that time were 5,745. 5,745 out of 11,429. Don't forget, this guy took 11,429 each year for 82 years. Okay, he observed. It's not as if he did that. He observed that. Okay, part of it he visited historical record as well. So the highest occurred in 1661. Highest ratio. Okay, occur in 1661. I think that should be 0.5362, and X as at that time was 6128. Okay, now according to this guy, now here this guy was using a constant probability, right, from year to year, it's believed that it's 1/2, 1/2. But this guy want to prove that the probability is not going to be constant, from year to year. Okay. Now this is the lowest. This is the lowest. This is the highest. Okay. Now, you know what I decided to do? This guy understand binomial because he believed that x as a random variable here because represent the numbers of males, okay, and there are two possible outcomes. It's either male or female, okay, that will be binomial. And the fact that he has more than one triad, this is for 82 years, that will be binomial, right? Okay, he now want to find the probability of x lying between the smallest 5745 and the highest 6128. That will be binomial. Okay, so which means I'm gonna go summation s start from 5745 to 6128. Okay, what is the sample size? 11,429. This is raised to power x, and of course, what is the p? It's 0.5. Okay, it's 0.5 raised to power that. Okay, and after doing that, you got this. This is approximately 0.292. 0.292. Okay, but let me tell you this. As at that time, this is difficult to get. That time, no technology, if you can compare to now. Okay, this is using binomial. Okay, now, if you take a look at this, it took him, this person, this guy happens to be, there are few people who can actually compute this as at that time. Okay, now at the end of the day, he believed the probability of the difference in birth ratio, okay, the probability of the difference, okay, in birth ratio to be is 0.292 raised to power 82 instead of this. Okay, now when you take a look at this, right, because this is very difficult to do, and that was why De Moivre in 1733 was now looking for a distribution that can approximate binomial, and the work of De Moivre is normal approximation